So I want to talk a little bit about something that you might have noticed in the first lecture that I did, that you've already watched, but I just want to go back. Normally what I do is I kind of open up the class, and if we're in class, there's usually like 3 different sections. And what I normally do is I go and I point. So who's going to die? That's what I just did. And the question I have is, why do we live so long now? Even though we're going through a plague right now, I never thought I'd see the day when we actually, well, that's not entirely true. HIV has been a plague, but it's a little bit different. It doesn't kill people right away. And so before it kills people with HIV, usually it's transmitted by sexual activity, or sometimes by bodily fluids. Okay, so we have gone through a plague recently, which was HIV. But in terms of a plague like in yesteryear, so here we have a picture of, let's say, the plague, the Black Death in Europe, which showed up in the 14th century, I think 1347 or something. There's still some question about when it arrived, where it arrived, what actually, how it was transmitted. It was thought that perhaps fleas on rats were the vector. It's called a vector-borne disease, and the fleas carry the disease, and they bite people, and they bite other rats. There's some question now whether that's actually true. I have seen the plague up in Lake Tahoe region, where I used to do my PhD. Ground squirrels up there, plague is endemic, bubonic plague. And I remember one year, the plague hit where we were at. We had a field station up there. And we were finding dead rodents all over the forest, dead and dying rodents. It was real obvious. You couldn't miss it. And when the plague actually struck in Europe, people weren't finding dead rodents. So there's a question of what was actually going on. And it looks more like now that perhaps the plague bacteria was actually transmitted through lice, hair lice, between people. Okay, so turns out that they can be transmitted that way as well. Okay, so back, let's say 150 years ago, and before that, the average lifespan was about 40 years old. There was really, really, really high infant mortality. Sometimes 50% or 60 or 70% of infants died within their first year. Either they died during childbirth, along with their mother, or they got sick. Usually infants don't have a very good, well-developed immune system. And so a lot of infant mortality, even today, if you go to some places like in Africa, where there's not much modern medicine, infant mortality is still pretty high, and usually dies from either respiratory infection or a digestive infection. Okay? And then very few, let's say half, made it to adulthood. Not all of them actually bred. And so death was a big deal, um, from 150 years ago all the way back. Okay? And life was really kind of, there's a guy named Hobbes who was a philosopher, and he had this saying about life was short and brutish. And it was pretty miserable. And so I normally ask, okay, why are things different nowadays? And I list a bunch of different things. One is sanitation. Actually, um, better food, uh, modern medicine, and then perhaps less violence. I know it looks like there's a lot of violence. We're much better at killing people nowadays, but if you actually go back in history, you notice that people were pretty much, it was a very violent society almost everywhere. Not everywhere, but most places. The big thing was that up until, let's say, 1850, no one really understood what caused, let's say, infectious disease. An infectious disease, kind of like what we have now, COVID-19, is some microbial pathogen or a bacteria, a virus, a fungi, a mold, something like that that can cause disease. Okay, and those were the big killers in the past. Obviously, there was no antibiotics. People didn't even know what was actually causing disease back then. There was an idea from the Greeks that it was bodily humors, kind of like what's going on with Chinese medicine today, that things are out of balance and that's why you get sick. And then there was something called miasma, like there was an idea that you could catch disease and it was in the air, but they didn't know where it was. Okay? So, like malaria is actually mal is bad and the area is air, bad air. And it always happened in the summertime, usually, when there's mosquitoes around, but people didn't realize how it was actually transmitted. Okay. So the real change was finally beginning to understand in the later 19th century, from 1850 or 60 on, with Edward Koch and Louis Pasteur, and it was called the germ theory of disease. And by germs, they meant, by this time, they knew what bacteria was. They didn't know about viruses. They couldn't see them. You can't see them with a light microscope. But you can see bacteria and mold and cells and things like that. And microscope was invented in, I guess, in the beginning in the 16th century in terms of modern optics. But people finally supposed that perhaps these things that we're seeing under the microscope might be causing disease, and it was shown that was the case with Koch and Pasteur. Okay, and when people started to understand that, they understood that perhaps there was a guy named John Snow in London. There was an outbreak of cholera, which is an intestinal disease. It kills lots of people, mainly from dehydration. And he actually showed, in terms of, he was basically the first epidemiologist, he showed that there's a cholera outbreak and it was all centered around one well where people were getting water in London in 1850 or 60, something like that. And he showed that all the people who were getting sick from that one area. And then they showed, in fact, that water there was contaminated with cholera bacteria. Okay. Another thing that people knew, obviously, was food. And one of the big killers, up to a certain point, and still even now, is famine. You still get famines occasionally in underdeveloped countries. And so, better food, in other words, getting enough calories, forget about whether it's good food or not, just basic calories, having enough to eat, goes a long way in allowing you to survive better. Okay? And then there's modern medicine where, some real changes. I would say the beginning of antibiotics in in 1950, right after World War, or during World War II, but mainly afterwards. And so nowadays, there's all these, we have much better sanitation, we have much better food, even if you eat really badly, like having double doubles from a hamburger joint or whatever, you're still at least getting enough calories. Okay, and one of the problems before was not getting enough calories, being malnourished. And then, of course, violence, and things are much less violent nowadays. So, you might be asking, well, why am I actually asking this question? And it's simple. Or why am I going through all this? Things have changed. Most people in this classroom, if we were in a class, if we were born 300 years ago, most of you wouldn't be here. I wouldn't be here either, probably. Most of us would have died in childhood. And life would have been pretty brutal. Okay? People didn't live that long. So, obviously, in terms of the average lifespan, a lot of it had to do with a lot of babies dying, so that kept everything down. There were still some people that lived until older age, 60, 70, 80, 90, even 100. Let's say back, all the way back, let's say to the Greeks. But the percentage of people who actually lived that long was very small. So nowadays, if you make it to, let's say, the age of 20, there's a good the average lifespan, if you make it to 20, is probably 80 or 85 or something like that. Okay? In other words, half the people, if you looked at something called the median, which is half the people above, older, and half the people less than surviving to a certain age, in their 80s or 90s. Okay? Obviously, some people still die earlier. Let's say they get cancer, they have heart disease, these are chronic diseases, or they get COVID-19. Well, other people somehow, but nowadays, up to 50% live almost till like the average lifespan in the United States is about 80 years or 78 years, which is less than the United States than, let's say, in most of Europe or Japan. We're a little behind the times. There's a number of questions why that's so. But anyway, you live, at least half the people live to, let's say, 78 years old, and then half of those manage to go even longer, and others, of course, don't live as long. Okay, whereas in the past, maybe 10% of the people who were originally born make it till 80 years old. Okay, much smaller percentage. So, things have changed drastically in terms of the lives you are living nowadays. And the whole reason that you are actually alive today is because of modernity because of science. Okay? Now, it turns out the government, since World War II, before that, not so much, but um, after World War II, uh, the U.S. government started spending lots and lots and lots of money on science, on modern medicine, medical science, but also on physics. A lot of it was technology, but a lot of it was actually basic science, where you understand the underlying um, processes and patterns that are going on. And once you understand those, you can, let's say, for modern medicine, obviously, like the germ theory of disease, once you realize that germs are microbes, whether it's bacteria or viruses or whatever, are causing infectious diseases, then you can actually do something. You don't know that that's what's causing it. The basic science that there's a microbial organism, some of which cause disease, then you can't do anything about it. So that's basic science. Once we understood that, in the 19th century, things started to change rather drastically because we suddenly knew at least what was causing disease, and we could take it from dump things in the middle of the street. Sewage went right in down in the middle of the street. It washed all over the place. Everybody got infected with all kinds of stuff. It was really, really, really dirty. And nowadays, obviously, that's not. So there was a basic understanding of science, and the same thing is happening now. A lot more. We understand much more. But it's not just why do we do science? We do it well as for helping human beings, but a lot of it, the big stuff, is really just human beings being curious. And the useful stuff is a minuscule amount. It's very important, obviously, but everything really comes from basic science. And so if we don't spend that kind of money, we don't get the advantages of good science that we've gotten. Everything now from material science, computers, all kinds of things. It's all based, like computers and modern communication, it's all based on physics. In fact, a lot of it's based on quantum physics and stuff that Einstein discovered back in the early 1900s. Okay? Einstein never invented anything in his life. He just wanted to try to figure stuff out. And the things that he figured out actually could eventually be turned into something useful like technology. But he wasn't really concerned about that. He was just trying to figure out what the hell's going on. Okay, so a lot of politicians don't seem to understand, or they seem to think that we should only fund things that'll actually help human beings. But we can't do that unless we understand the underlying things. So that's what I was trying to get across. I'm going on more than I wanted to. Okay, so in the future, you should ask your politicians who you're voting for, do you support science? Because that's having the biggest effect. Now, I'm not saying that poetry and music and humanities is not important. It is. But most of us we're alive today basically because of science. And not just recent science, but things that have been learned. A lot of the stuff that we've actually learned is based on stuff we learned a long time ago. Like a lot of mathematics that we use today was first discovered or figured out by mathematicians, let's say, thousands of years ago with Archimedes. Okay, so we have knowledge that we've based on. But when a politician says science isn't all that important, or why don't we just fund things that are going to help us, you should ask them why they're still alive today, and then explain that they probably shouldn't be if it wasn't for basic science. Like this. Section 1 is up here. Section 2, Section 3. Okay. And normally I just point and say, okay, you're alive, you're dead, you're dead, you're dead. And so in the first section, let's say there's 10 people. 7 of them are died. In fact, we'll say that 6 of them died as infants. And then another one died, let's say when they were in their teens, just about the time they were sexually mature. And then the second section, 4 of them lived. Another one actually lived until they were older, but they never had any children, so they were as good as dead. Okay? So, in other words, there were 3 out of 10 survived. 4 out of 10 survived. And then here, we'll just say that 0 out of 10 survived, or 10 out of 10 died. Mainly because there was a plague. And it wiped the whole village out, right? Just like for that section, we'll say something came along and wiped you all guys out. Okay. So, and the question is, well, let's go back. Okay. So, what constitutes a scientific hypothesis? First of all, we usually ask a question like, why do we see certain things, observations, and what's an explanation for those observations? So I kind of went over the thing where the rising sun, and in the earlier lecture that you watched, the rising sun and all that. And I said, well, the intuitive hypothesis is that the Earth is the center of the universe and everything revolves around the Earth, and we know that's not true. But I did it so that if you didn't know anything, and it was all based on, let's say you woke up, you didn't, and you realized you were laying next to what's called a river, and the river is going from one direction to another, and then the sky starts turning lighter and lighter, and eventually the sun rises, and all that, and it looks like, and it goes around and around and around. It looks like it rises in the east, sets in the west, disappears, it gets dark, and then rises in the east again, and sets, and it looks like we're the center of the universe. And most people thought that was true. So you can have something where let's say everybody believes a certain thing, but that doesn't make it true. Okay? In fact, now we know that the reason it looks like the sun is rising is not because the sun is rising. The sun's not moving. The Earth is moving in relation to the sun, first orbiting the sun. Takes a year for one orbit. And also, the Earth is rotating at about a little over 1,000 miles an hour at the equator. So it makes it look like the sun is rising, but it's not really the case. Okay. So we see things, we ask a question, why is this? We come up with an explanation, and then we actually test an explanation by testing the predictions that it makes. So a good example of this is, let's say I have keys in my hand, metal keys, and I hold them up in front of the class and I drop them. And where do they go? They fall to the floor. Okay? And then I ask you, what do you see? And then what's the explanation for it? And you say it's gravity. Okay. I say instead, I have a different explanation. I have a different hypothesis. In fact, it's a wild hypothesis. It's pretty much stupid hypothesis, but it's still a scientific hypothesis. And why is this scientific hypothesis? It's because it can be tested. The predictions can be tested. So I dropped the key. I said, the reason we actually have gravity is there are metal-headed human beings in the center of the earth that cause gravity with their heads with magnets. Now, it turns out one of the forces of nature is electromagnetism. Another force is gravity. There's two other forces, but we'll forget about those for now. And my explanation is that the keys fall to the ground because of these metal-headed, magnet-headed people and electromagnetism, magnetism. Okay? But that accounts for gravity. But the thing is, so the prediction is that things fall to the ground. But what does magnetism actually work on? It works on metal objects, certain metal objects. It doesn't work. It doesn't make things fall to the ground or whatever if they're not made of those metallic objects, right? So how come we don't go flying off into space? So the prediction is, if the metal-headed people are causing gravity through electromagnetism, then only metal objects should fall to the ground and everything else should be floating off into space. That's the prediction. Is that the prediction we see? No. So we didn't run an actual experiment per se, but we still use predictions and observations to test that hypothesis, and we could show that that was wrong. Now, if in fact we had, if let's say we had, well, let's say electromagnetism and gravity were the same thing, that would have been a different prediction that you could have tested. Okay? So, as Einstein said, no amount of experimentation can ever prove me right, but a single experiment or observation can prove me wrong. Okay? It's a very, very, very stringent test.